Okay, folks. So my floating controls disappeared. Give me a second, folks. Zoom seems to have messed up, so I can't see my controls anymore. I'm going to have to quit and come back. Hello, can everybody hear me?
Yes.
Good. Wait. Let's start it. Let's begin. We have completed our series of lectures on the basic idea of neural networks, multi-layer perceptrons, and how we can train them. So now we are moving on to our next series of topics, namely convolutional neural networks. So the story so far, MLPs are universal function approximators. They can model Boolean functions, classifiers, and regressions, and they can be trained through variations of gradient descent, for which gradients can be computed by backpropagation. And the kind of model we've looked at so far was like this. It was a multi-layer perceptron, where you received some inputs and pass these inputs sequentially through many layers of neurons until you computed your outputs. And these could recognize patterns in data, any kind of data like digits or any other kind of vector data. So now we have a new kind of problem. I have, say, a recording of this kind. I know the length, it's always 1 second long. And I'm asked to determine if the recording includes the word welcome. When we get a recording of this kind, the first thing you do is to convert it to a sequence of vectors, like a spectrogram. And then if it's just a problem of classification, and we were to treat this using standard classification strategies, we just construct an MLP, which looks at the entire input and tells you if the recording contains the word welcome or not. But then my question to you guys is this. Suppose I've trained a neural network that can recognize the word welcome when it occurs in the initial portion of the recording over here. Will the same network also recognize that the recording includes the word welcome if it occurs in the second half of the recording like so? What do you guys think? Would a network that detects welcomes and recordings of this kind also perform well in recordings of the second kind? What do you guys think? So, see, no, right? Why no? Why not necessarily? The correct answer is no. And it has to do with the fact that, let's say you thought of this recording as a vector. If I unravel the vector is going to look something like this, right? Then in the first case, the pattern appears over here. So you can think of this, if I were to reduce it to a series of zeros and ones, it would have zeros here and ones here and zeros here. In the second case, this recording is going to become a vector of this kind, where the pattern occurs here. So if I were to reduce it to zeros and ones, you'd have zeros out here, including in the locations where you had ones in the previous one. And the ones would be down here. So these two vectors are entirely different. If you were to think about it in 3 dimensions, this is like the x-axis, this would be the z-axis or something of that kind, right? So these two recordings are completely different just by changing the position of the target pattern. So what we need is a simple network that will fire, that will say yes, if the recording includes the word welcome, regardless of the location of the word. And if the recording doesn't include welcome, it should say no, it should not fire. Similarly, consider images. Suppose I were to train a network to detect flowers in images. Then, if I were to train a network that could recognize flowers if they appear in the top left corner, would the same MLP also give you the correct answers if the flower was in the bottom right corner? Would it do so? Yes or no? What do you guys think? No. Why not? Again, why not? Different vector representations. They are in different positions, which means this vector is entirely different from this vector. So once again, we need a network that will fire regardless of the precise location of the target pattern. So these are examples where the location of the pattern is not important. The location of the flower is not important, or the location of the word welcome is not important. Only the presence of the pattern is important. And conventional MLPs are sensitive to the location of the pattern. So if I move the whole location by just one component, as far as the vectors are concerned, the vectors are entirely different. They live in different subspaces, and the MLP won't recognize it. What we need is a network that's shift invariant, meaning if you shift the target pattern around in the input, it should still fire. So, can anybody suggest how we could build such a network, which is shift invariant for, say, the welcome problem? How would we do this? Anyone? Data augmentation. So explain data augmentation. You would say, so you're suggesting that I can provide training data with welcomes in every position. And then if I do so, then it would actually learn to find welcome everywhere. The problem is you're going to need a really large network for it to be able to recognize the word welcome in every possible position. And you're going to need an enormous amount of data in order to, with welcomes occurring in every possible position. So yeah, it's a reasonable solution, but it's not a very meaningful solution. A better solution is as someone mentioned, to scan. So you can build an MLP that recognizes, let's say you know the approximate length of the word welcome, then you can build an MLP that looks at an input of that size. And so you can use it and now try to detect if the word welcome occurs here. And then scan the input for the word welcome. And now this network, the scanning is going to produce one output at every position, right? So if it produces, but my question is, does this entire recording contain the word welcome or not? What I got was an answer at every position. So how do I combine all of these to get one answer? Anyone? How would I combine these? Or, perfect, right? So the correct answer is OR. How would you do an OR in this case? How would you do an OR in this case? Anyone? So here's what happens. If the recording contains the word welcome, then at least one of these positions, this output is going to be very close to 1. If the recording does not contain the word welcome, at none of the positions will the output be close to 1. Does that give you a hint how I could combine these outputs? Anyone? That give you a hint? Take the maximum, right? And so not the argmax, the max. And if any of these is high, then the overall output is high, and if the overall output is close to 1, I know that the recording includes the word welcome. That makes sense to everybody? And if there's no welcome in it, the max will be small. And so you can say the recording doesn't have the word welcome. Now, you don't need to have a max. The max can be computed using a perceptron, right? We know this. And if you want to account for small bits of variation and the scale of things, then you could even have an MLP out here. But the basic idea remains the same. You detect a welcome detector and then construct a welcome detector and then scan the input, produce an output at each position, and then combine those outputs using a max or a softmax or an entire NLP. And that's going to tell you if the recording contained the word welcome. Does this make sense to everybody? Yes or no? Right. So how exactly did we do this? Somebody asked me, what do you mean by scanning? Here's what you do. You would go through the input. So the input is long. So you're going to start from the first position and go left to right. At each position, you're going to chunk out a little segment. And then you pass that segment through an MLP. And so this MLP is going to give you an output for this position. So you do this for every position. You're going to get an output at every position. And this collection of YTs is then put through the softmax to give you the overall output. So is the pseudocode making sense to all of you guys? What we're doing here? Yes. So, okay. Well, if it contains more than just one word, just the word welcome, if it's a welcome detector, it's not going to fire for the other words, other instances, other words. If you have more than one instance of welcome, that's great too. It means the recording includes the word welcome. So just see, because if the recording contains the word welcome, then at least one of these is going to be high. So if I look at the max tells me that there was at least one. And if the max is 1, it means that there was the word welcome was detected at least one position. That answer you, Jesse? Okay. But then it's actually just one giant network. How so? These are all little networks looking at little windows of the input. Their outputs are being combined through a softmax or a perceptron or a multi-layer perceptron. So does this whole thing not look like just one big network? If I were to just draw this, this would be just one big network. Would it not be? Yes or no? So what's the distinction between this and a regular network of the kind that you've seen before? What's the difference? Anyone? So the difference is that at the lowest layer, you have many copies of the subnet, which is basically this network scanning the input. And so the network itself has many subnets, each of them looking at a different portion of the input, and all of these subnets are identical. You're training the whole network. That makes sense to everybody? That these, right? And of course, by doing this, this network has become shift invariant. So this whole thing is just like one large network. This is the final layer of the overall MLP. I can just write giant MLP out here, right? So those subnets are proportional to the length of the pattern that you're trying to detect. If I want to detect if the image contains a flower, I could construct an MLP to look at a region of the input that corresponds to the size of the flower that I expect to detect. And then I can scan the input for the flower. And I'm going to get one output at every position in the image. And then I could just take a max over all of these, or maybe put it through a softmax or a perceptron. And the overall output is going to tell me if this image included a flower or not. That makes sense to everybody? Right. We just did. So again, here is the pseudocode. Now you're going from left to right, but you're also going from top to bottom because you're scanning the input like so, right? And then at each position, you're chunking out a little window, which is this guy, and you're passing that window through an MLP. That's going to give you one output for that position. So you get outputs for every position. The collection of outputs is now put through a softmax that gives you the output of the overall network. So this pseudocode explaining things to you guys. Does this make sense to everyone? Okay. Once again, this is just one giant network, right? This entire operation. You have little subnets looking at different windows, and they all connect to a final softmax or an MLP. And so this is going to be this is just one giant network with one key feature. All the subnets are identical. And so this network is shift invariant in that if you move the basic pattern around, it's still going to give you the same output. Right. So do you see how this is shift invariant? This guy. Yes or no? Right. Okay. Do respond, guys. And so in the 2D case too, this whole thing is just one network where this is just the final layer of the overall MLP. I could just write giant MLP and everything works, right? So that's it. Now here is your first poem. All right, guys, 10 seconds. 10 seconds. Let's stop it right here. What's the answer to the first question? True or false? First one, true or false? Second one, true or false? Perfect, right? Both statements are true. Now, I'm going to just change the picture a little bit. I was showing MLPs in this manner, this layered network. And so when I was visualizing scanning with an MLP, the picture I showed was something of this kind, where the same MLP analyzes the input at each position, and then those things, their outputs are combined for the final overall output, right? But then this kind of illustration has a problem. The x-axis in my example represents time. So if I do this picture like this, it seems to give the impression that this yellow neuron is computed after this red neuron. So it seems to give an impression within each layer, but that's not true. What happens is that the entire network is computed at each position. So rather than an illustration of this kind, this is a more valid representation. This first layer is computed on some input. This is the second layer. All the neurons in the second layer are connected to all the neurons in the first layer. All the neurons in the third layer are connected to all the neurons in the second layer, and this entire computation is done at one position. So can you guys see why this is a more appropriate illustration than this one? Can you guys see this? Yes or no? Because this seems to indicate that this is time, but it's not time, right? So I'm going to use this illustration. And I'm going to simplify things a little bit further. I won't actually draw all these arrows. I'm just going to draw a simple arrow of this kind. What this means is that these layer 1 neurons connect to all the inputs between these two positions. All the neurons in the second layer connect to all the neurons in the first layer. All the neurons in the third layer connect to all the neurons in the second layer, and so on. They're scanning, when visualized in this manner, is actually going to look like this, where I'm scanning, I'm looking for a pattern, which is 2 inputs wide in this example. And so this entire network is analog inputs, then it's stepping forward by 2 time steps, and then analyzing these 2 inputs, then stepping forward by 2 time steps, and then all of their outputs are going into the final decision layer of the network. So is this illustration making sense to you guys? Yes, sir. Yes or no? Okay. And here's what you'd get if you were stepping forward by 1 time step instead of 2. This is what an actual scan would do, right? So again, going back to our lecture, when I'm scanning a picture, I am scanning the input with an MLP, and basically I'm computing the same MLP at every position. All of their outputs are going to the final decision layer or network. Similarly, in the 1D case, when I'm scanning some, say, like a speed signal, I'm scanning the entire input with the network, and all their outputs are going into the final decision machine. So but then these things are just giant networks. And once you realize that, you realize that you can just train them using backpropagation, using conventional backpropagation. So if I want to train a flower detector, I don't actually have to mark out the position of the flower. I can provide a collection of images with and without flower positions. Or no, I can just have a collection of recordings with and without the word welcome in it, and that should be enough to train this network. I don't actually have to identify where in the input the word welcome has occurred, because this scanning bit has been figured into the overall network itself. Yet in the process, you will somehow magically also learn the lower level flower or welcome detector. This making sense to everybody? What we just said? I see a single yes. What about the rest of you guys? Okay. So, one thing, when you're training the network, you have to take into account something else. You have to take into account that all of these subnets are identical, right? So, this is what is called a shared parameter network. If I train this network and I make an update to this subnet, the same update must be made to all of these subnets, because it's the same subnet scanning the entire input. Similarly, if I make an update to this guy, that update has to be reflected in all of these because they're all identical. That makes sense? Yes or no? To all of you guys? Okay. So how does that math work? Right? So these are all shared parameter networks. These lower level subnets are identical. So any update to one copy must equally update all the copies. Let's see how that can be done. The way we do it is, I'm going to generalize this. How many subnets? You don't need, you're scanning, right? So it's going to depend on the size of the input bracket. Anyways, let's consider this. These are all special instances of what are called shared parameter networks. What is a shared parameter network? A shared parameter network is one where you decide for some reason that some subsets of parameters must have identical values. For example, if I decide that these 2 edges in this network must always have the same weight for whatever reason. What does this mean? That this edge equals this edge, and both of them equal some common shared value. So when I make updates, I won't be making updates to this guy. I will actually be making updates to the shared value, which will get copied to both of these guys. Is this making sense? The notion of a shared parameter network. Right? So how does that work? How does a shared parameter network work? Here's what happens. This shared parameter WS directly influences the shared value, directly influences both these weights. And both these weights influence the divergence, right? So when I want to compute the derivative of the divergence with respect to Ws, I have to take derivatives down both paths. So the derivative of the divergence with respect to Ws is going to be the derivative of the divergence with respect to this weight times the derivative of this weight with respect to Ws plus the derivative of the divergence with respect to this weight times the derivative of this weight with respect to Ws. So that's what this equation shows, right? But then I'm literally copying this guy over here. I'm copying this guy over here. So what is the derivative on this edge? What is the derivative of W lmn with respect to Ws? What is this derivative? Anybody? 1. Similarly, what is this derivative? That's also 1. So these guys just become 1. And so the derivative of the divergence with respect to the shared value simply becomes the sum of the derivatives of the divergence with respect to each of the terms that share that value. And so for any given training instance, when you pass the derivatives down, you're going to get some derivative over here and some derivative over here. They need not be identical, but then you sum them up to get the derivative with respect to the common shared Ws. And then once you do that, you can use that derivative in the update. So overall, when you're performing training, so we would have, Christian, how is it? I'm saying WL equals WS. What is the derivative of WL with respect to WS? Christian. If you have this relationship, what is the derivative of this guy with respect to this? What would it be, Christian? It's got to be 1, right? If A equals B, d over dA is always 1. So now if you have a network of this kind, then in your shared parameter network, you know that these guys have identical weights, right? Similarly, you know that these guys have identical weights. So you have many sets of edges which have the same weight. So I would be computing the derivative of the divergence with respect to this common value for all of these guys, which is simply going to be the sum over all of these edges which share this common value of the derivative of the divergence with respect to these weights. And that is what you'd use to update your network parameters. So for every set S, where all of these red guys are one set, all of these blue guys are one set, and so on, you want to compute the derivative of the loss with respect to the shared value. Then you want to update the shared value and then copy the shared value over to each of the W's. And then what is the derivative of this loss with respect to the shared value? The derivative of the loss with respect to the shared value, for that you go over all the elements in the set and sum the derivatives of the divergence with respect to those elements. So for example, here, if these guys have a shared value, then you'd be going over all of these guys, compute the derivative of the loss with respect to each of these guys, and sum them up. And when you sum them up, you're going to end up with the derivative of the loss with respect to the shared value. And that derivative with respect to the shared value is what you would use in the gradient descent. And then having updated Ws, you'd copy Ws back into each of these guys. So did this make sense? What we just did over here. Right. Okay. I got a few yeses, so I'll say. And of course, the derivative of the divergence with respect to any one of these guys is computed using backprop. So the story so far, position invariant pattern classification can be performed by scanning, 1D scanning for sound, 2D scanning for images, but you can have work in higher dimensions, 3D and higher dimensions for high dimensional data. Scanning is equivalent to composing one large network with repeating subnets. So the large network has shared subnets. And learning in the scan network is performed using back propagation, but backprop rules must be modified to combine gradients from parameters that share the same value. Now, this applies for the model which I just saw, but it applies in general for networks with shared parameters. So, any questions so far? Any questions? Any questions? If not, I'll go on. I'll wait for 5 seconds for questions. Okay, if not, let me continue. Okay, what is 1D scanning and 2D scanning? So I'm scanning here in 1D. I'm just going along time. John Didier? And here I'm scanning in 2 dimensions, right? So why is W's have to equal to each weight? I'm not sure what that question means. So Farnaz, how did you construct? When I'm scanning here, I'm just scanning in 1 dimension, right, Farnaz? Right. Yeah. So whereas here I'm scanning in 2 dimensions, right? And I'm not sure who WCJ is, but then if you want to train one large network, you'd need to, the network would be, what is scanning, Uviman? When I'm scanning, I'm using one network here. I'm using the same network out here, right? So if I'm using the same network, it's like having 2 subnets with identical parameters, is it not, Vimana? That's what it is, okay? I'll go on. If you have any other questions, just hold the thought till after class because we need to move on, okay? We have a lot to cover. So here is what we were doing now. I'm using this network. In my example, I have 4 neurons in the first layer, 2 in the second, 1 in the third. And then so if I were to use my vertical representation, here is what the picture would look like. And then we were scanning the input using this network. So at the first position, what happens is that first, the 4 neurons in the first layer would compute their outputs. Then the 2 neurons in the second layer would use the outputs of the 4 neurons in the first layer and then compute their outputs. And then the 1 neuron in the third layer is going to look at the 2 neurons and outputs of the 2 neurons in the second layer and then compute its outputs. So is this computation making sense to you guys? Yes or no? Is this illustration making sense? Okay. So assuming it's making sense, then what happens? These values are computed at the first position. Then the entire network moves 1 step. And those values are computed at the second position. Then it moves 1 step. It reads a different section of the input, and these values are computed at the third position, and so on, until you compute these values at every position in the input. And then, of course, all of these final outputs are combined into a softmax. This is the overall computation performed. These are all the values computed. Is this making sense? This picture, everybody? Okay. Now, here's my question. Let's say I place the network in the first position and the first layer computes its outputs. But the first layer is in a hurry. It doesn't wait for the subsequent layers to compute their values. It just runs off and computes all of its values before the second layer even jumps into action. And then the second layer and the rest of the network read the values that this first layer computed in the first position and process them. Would this value be any different than if the entire network had been computed over here before it moved on? Would this value be any different? It should not, right? Because the values are going to be identical. So the output here does not change due to the reordered computation. But then, now the second layer gets inspired by layer 1 and says, you know what, I don't need to wait for layer 3. And it goes off and does its computations from the outputs of the first layer. And then the third layer operates on the outputs of the second layer at this position. Is this guy going to be any different than if I had computed the entire network here before moving on? No, right? And so now the third layer can go off. The output here doesn't change due to the reordered computation. And then the third layer can go off and do its thing. And you can put the whole thing, through the softmax, right? So we just changed the order of the computation. How does that look like in terms of code? And you agree that changing the order of the computation is not going to change the output of the softmax here. Do you agree with that? Yes or no? Okay. So what really happened? It may make more sense if you look at it through code. In code, we've scanned the input at each, if you were just looking through at this example, you scan the input. As you scanned, at each position, you pulled out a segment, and then you put it through the MLP and computed an output at this position, right? If I expand this out, it's going to look like this. You're scanning the input. At each position, you're taking this input, and for the first layer of the network, you're looking at this entire section. And from this entire section, you compute a Z. From the Z, you compute a Y, right? Then you go through the next layer. The next layer uses this Y to compute its Z, and then it computes its Y. Then the next layer uses this Y to compute its Z and its Y, and so on. So what has happened is that at each position, you're going through all the layers of the network, right? Is this code making sense? Okay. Now, but all the action is happening inside the innermost loop, is it not? All the actions happening inside the innermost loop. Yes or no? Right. So if I change the first loop is over time, the second loop is over layers. Actions here. If I change the order of the two outermost loops, if I put L first and T next, would it change the overall computation of this algorithm? Keeping in mind that all the action is really inside the innermost loop. It would not, right? So that's basically what we did. We scanned the input. We scanned the input with each layer before moving on to the next layer when we did this computation. That's what happened over here. That makes sense to everybody? Right? Yes, okay. So same thing in 2D. I'd be scanning the input for the desired object using an MLP. This is my input. There I have some hidden layers, and then there's a final output layer. So at each position, the network computes an output. This is the set of outputs computed from each position. These guys are put through a softmax or something more complex maybe for the final decision. But then what's happening at each neuron? At each position, the first layer neurons are looking at all of these values and computing an affine value and putting it through an activation, right? So let's look at this first guy. Like in the 1D case, this guy, he's in a hurry. He doesn't wait for the rest of the network. He goes off and computes his entire input, right? In fact, it's not just him, but all of his siblings, they do the same. So these 4 neurons go off and compute their output values without waiting for the rest of the network. So now, if I want to find out if there's a flower in this position, what would I do? If I want to find out if there's a flower in this position, what would I do? Anyone? What would I do? Somebody. I verify all the results. I need to look at the value that each of these neurons computed when they were scanning this location. Those would be these 4 guys, right? And so these 4 can now be put through the rest of the network. And that would tell me if there was a flower over here. That makes sense to everybody? Yes or no? Right, Umana, that makes sense to you? Right. Okay, I'm assuming it did. So at each position, each of them this guy is computed, for instance, on this position. So also this guy is computed from this position. This guy is also computed from this position. These 4 are computed from this position, and so on. That answer you, John? Okay. And so to classify a specific window, I just pick up the first level activations from those positions corresponding to that, from the outputs corresponding to that position, and pass them on to the next layer. But then I can recurse the logic. The second layer neurons don't need to wait for the output, right? The second layer neurons can now scan the outputs of the first layer neurons. But then keep this in mind. The first layer neurons, they were just looking at the entire input. Each neuron was looking at all of these guys in the input, right? The second layer neurons are simultaneously looking at the outputs of all the first layer neurons in that position. That makes sense? That the second layer, what the second layer neurons are doing? This guy has to look at the outputs of all four neurons, so it has to look at all four of these guys. Make sense? Yes or no? Okay. So, Christian, how do you know the number of you're scanning? So it's going to depend on the size of the input, right? And so now the second layer neurons can go off and scan the first layer neuron outputs. And then if I want to find out if there was a flower over here, I just read the outputs of the second layer neurons when they were looking at these positions in the outputs of the first layer neurons. And these are the outputs that the first layer neurons produced when they're looking over here. And so now the output of this neuron is going to tell me if there was a flower over here or not. Did this make sense? Did this illustration make sense? Okay, so that's what we will do. And so we can recurse it and we can make a map for the third layer neurons itself also. The map is a flower. This neuron, which scans these two outputs simultaneously, is creating a map for each location of the original image, right? Yes, yes, here. So each of these neurons is scanning the input. Okay. How do you find the corresponding position? If I look at this guy, this one came from here and here, right? And these came from here and here and here and here. And each of those four came from here. So you can just work your way back and find out where they came from, if you're interested, right? And so to detect a picture at any location, you only need to look at the corresponding location in the output map. And of course, you can put the whole thing through a max or a softmax to decide if the picture has a flower. Right? And very often, instead of drawing this as a map, we'll just draw this final layer output as a flat, as a flat layer of outputs, flat arrangement of outputs. It's called flattening, and these are put through max, softmax, or an MLP. So what happened over here? Again, when you were scanning, you were going over X, you were going over Y. At each position, you were pulling out this was your image. You were going over X, you were going over Y. At each position, you pulled out a segment, you passed it through an MLP, and you got a Y value over here. And the collection of Ys was put through a softmax, right? But then if you look closely at what's going on, within each position, you're going through the layers. At each layer, for the first layer alone, you're looking at a region of the input. But then from this region, you're computing a Z at each position. Each layer is computing a Z and then a Y. Then the next layer is looking at the Y to compute its own Z. And then it's computing its own Y. And then the next layer is computing the affine term and its own Y, and so on till you get to the end of the network. All of this is happening. You go through the layers at each position. So once again, and then the collection of the final layer outputs is put through a softmax. So is this code making sense to you guys? Yes or no? Okay. Once again, all the action is in the middle, right? Is in the innermost loop, right? All the actions in the innermost loop. Which means if I change the order, the output should not change, correct? Yes or no? So the L can go out, the X and Y can come in, and the network's output doesn't change. So that's what happened over here. Each layer is scanning the outputs of the previous layer without waiting for subsequent layers. All we did was change the order of the computation. And you should still get the same output. So the story so far, position invariant pattern classification can be performed by scanning the input for a target pattern. Scanning is equivalent to composing a large network with shared subnets. The operations in scanning the input with a full network can be reordered as scanning the input with individual neurons in the first layer to produce scan maps of the input, and then jointly scanning the map of outputs by all the neurons in the previous layers by neurons in subsequent layers. So here is our second pole. These are true-false questions. I'm going to give you only 35 seconds. Ten seconds, guys. 5. All right, let me stop the polls. What's the answer to the first question? True or false? Second one? True or false? Also true, right? Both are true. Beautiful. So what's happening? In the basic network, in the original framework, the entire NLP was looking for a flower-like pattern at each location. So what happened? The first layer neurons look at this entire window to extract a window level features, because these neurons are looking at this entire window, right? So each of these neurons is going to detect a feature that's typical of a flower that the rest of the neural network can operate on to determine if there's a flower there or not, which means the neuron is responsible for extracting flower-sized features. Each of these neurons bears a tremendous responsibility. It must detect flower-sized features, and then subsequent with all the arrangements. And then the subsequent layers are just looking at single pixels in the outputs of the previous layers. Does that make sense? The first layer neurons are looking for this entire window, but the second layer neurons are only looking for a single pixel from the positions of these guys. The third layer neurons are looking just for single pixels over here. That's what was happening. Yes or no? This may, okay. So, and but then why is that, Uvimana? Because this guy is only looking at these neurons' outputs, right? These two neurons are only looking at the outputs of these two neurons at any given position, right? I have this window. If I'm trying to detect if there's a flower, these neurons will each produce one output. And then the second layer neurons are going to look at these four outputs. Yes, Vimana? Right. You could scan a pixel at a time, or you could jump. Okay, we'll get to that. But then I can distribute the pattern matching over two layers and still achieve the same block analysis in the second layer. How? The first layer neurons can look at a smaller section of the image, say this size, and then scan the input with this smaller window. Then the second layer neurons can actually, this first layer neurons will arrange their outputs in the same shape as the input itself. Then the second layer neurons will actually look at a window of outputs from the first layer neurons. So what happens? When this neuron looks at this window of outputs, it's effectively looking at all regions of the input that were invoked when any of these outputs were produced by the first layer neurons. So now, although the first layer neurons individually only looked at this much, the second layer neuron is now going to look at a flower-sized pattern. Did this make sense? Right. And so this guy is looking at these inputs. And so it's looking at every portion of the input that was invoked in computing any of these highlighted dots, which would be the entire flower-sized window. So the first layer neuron evaluates smaller blocks of pixels. The second one evaluates windows of outputs from the first layer. This effectively evaluates a larger window of the original image. And what has happened over here? this window has now been distributed over two layers. Now, the first layer neurons are no longer looking for flower-sized patterns. They're looking for smaller patterns, like, say, the size of a sepal or a petal or a stamen. And then the second layer neuron is looking at all of these outputs and saying, so let's say this guy detects flowers angled this way or upwards, right? And this guy is detecting flowers angled this way. And this guy is detecting something like stamens, right? And this guy is looking at petals angled this way. So sorry, petals. So then this neuron is saying that when this guy has fired at these two positions, and when this guy has fired at this position, and when this guy has fired in the center, and when this guy has fired over here, I get this kind of a pattern, which kind of looks like a portion of a flower. That makes sense? Yes, no? Right. Okay. And so what we did was we let the lower first layer neurons look for smaller patterns, and the second layer neurons combine them in position to make decisions about the larger image. And then the second layer neurons can scan the maps produced by the first layer neurons with windows to produce their outputs at every position. And now, if the next layer neurons must detect if there's a flower out here, it just needs to look at these outputs from the second layer neurons. This makes sense to everybody? Yes, no? Okay. So, and now to compute the third layer neurons can scan the maps by the second layer neurons, and their outputs can be combined using a softmax to detect if there's a flower over here. You're still scanning, but you're scanning with a shared parameter network with one minor modification. What is that, right? So this is exactly the same as before. But then within the network itself, you have further sharing of parameters. Why so? Look at the first layer neurons. The first layer neurons are looking at small windows this size. So so if I have this as my network, this black neuron is looking at each of these 9 outputs to produce these 9 outputs. This is like having 9 copies of this black neuron, one looking at each position. Do you agree? When this black neuron scans this portion of the input, it's like having 9 copies of the neuron, static copies, looking at each of these positions, right? So similarly, when the second neuron scans the input, it's like having 9 copies of the second neuron. When the third neuron scans this input, it's like having 9 copies of the third neuron. And then subsequently, when the next level neurons look at the outputs at windows from the first level neurons, they're actually looking at all 27 of these values. That makes sense? Yes, no? Yeah. So this is the network. But then within the network, these 3 9 neurons have the same parameters. These 3 9 neurons have the same parameters. And these 3 9 neurons have the same parameters. So the network that is scanning the input has shared parameters within itself also. So this is actually means that the network that analyzes individual blocks is itself a shared parameter network. That making sense? Yes, no? Okay. And now I can do the same thing over 3 layers. The first layer neurons can be looking at even smaller windows, regions of the input and scanning it. The next layer neurons can be looking at windows of these guys. When it's looking at windows of these guys, it's basically looking at the entire region of the input that's invoked in computing any of these highlighted dots. And so then the third layer neurons could be looking at windows of these guys. When they're doing that, they're looking at all portions of the input that are invoked in computing or any of these dots, which is to say, it's looking at any region of these maps which were invoked in computing any of these highlighted dots, and which in turn is looking at any region of the input which was invoked in the computation of any of these highlighted dots, right? So yes, this neuron is now looking at the full flower-sized image, but it's distributed the patterns in the flower over 3 layers. This makes sense? What we just did? right? So we're not compressing anything. We're just distributing the patterns, right? The final classification for the entire image views the outputs from all locations as seen in the final map, right? How does the recombination happen since the neuron layers scan the entire input? No, they don't, right? So this guy, it's and Jean the dude, let's wait for after class. Okay. So what happened is that we are still scanning the input for a flower, but the network that's scanning the input is itself a shared parameter network. And so once again, this entire network can be thought of as one giant network where the subnets themselves have shared parameters within themselves. This makes sense to everybody? Yes or no? Okay. So code-wise, what was happening? Earlier, you were scanning left to right. Within each section, you're pulling out an image. Within each position, you're pulling out a section of the image and passing it through an MLP and then passing the collection of outputs through the softmax. So when we changed the ordering, we were going through the layers. At each layer was scanning the input. The first layer alone was looking at an entire section of the input. Subsequent layers were just looking at one position, right? From the outputs of the previous layer. And so this was what we were doing when we were not distributing the patterns across layers. But now the pseudocode becomes even simpler. What happens is that the first layer neurons are looking at little sections of the input of this width. Then the second, then the second layer neurons are going to be looking at windows of the outputs of the first layer neurons. The third layer neurons are going to be looking at windows of the outputs of the second layer neurons, and so on. So this extra clause that we had earlier, which said that only the first layer was looking at windows and the rest were looking at individual pixels, even that went away, and the overall code became even simpler. Each layer first pulls out a window of input of values from the output of the previous layer and then computes the affine terms and output terms. So is this modified code making sense? Each layer scans the input. At each position, it pulls out a window from the output of the previous layer and processes it, right? So the question is, this whole operation of scanning with a window, this is what's called a convolution. And so this entire network is what is called a convolutional neural network. Overall pseudocode for convolutional neural network. That I showed that for the 2D case. What about the 1D case? Same thing, right? So in the 1D scan, it's called a time delay neural network. It's primarily used for speech recognition. The first layer, without distribution, the first layer is, if you're looking for the word welcome, right? Then the first layer would be looking for a welcome sized region of the input. And then subsequent layers would be working on the operation outputs of the first layer. But then when you begin to distribute it, the first layer is going to look for smaller regions of the input. Maybe you're looking for regions which are the width of maybe a single phoneme, right? And so the first layer neurons are going to be scanning the input over smaller regions of the input. And then the second layer neurons are going to be looking at regions of the input, right? They want to look at a larger region of the input. So if they want to look at a larger region of the input, they must now look at multiple columns from the output of the first layer. And then they may learn that, that if the first neuron fires over here, and the second neuron fires over here, and the third neuron fires over here, there's probably a hello, right? So they can actually detect that. That makes sense? Sorry, guys. Did this make sense to all of you guys? Okay. And so The second layer neurons will be looking at a region of the first layer outputs. They're going to be looking at a bigger region. And what is the benefit over here? Instead of having the first layer neurons look for hello-sized patterns, the first layer neurons could now be looking at individual phonemes. And the second layer neurons can now combine these to make global decisions about whether the word has occurred or not. Right? And you can just, and so the second layer neurons are going to be looking over at this sized windows. You can distribute this further. The third layer neurons could be looking at regions of the second layer outputs, where each of these is looking at a region of the first layer output. So the overall region of the input that the third layer neuron is looking at is much wider. And so now you can, instead of be burdening just the first layer neurons with trying to detect welcome sized patterns, you can distribute the patterns and look for smaller units like phonemes or things smaller than phonemes and compose them into the overall pattern that looks like the word welcome. That makes sense to everybody? And so that's what we do. This is the 1D scan version. And of course, the final aggregator, which could be a perceptron, aggregates the output to say, does this recording have the target word, which could be welcome, right? This is what's called a time delay neural network. A 1D scan network is called a time delay neural network or a 1D CNN. So that leads us to the third poll. "45 seconds, guys." So, Georgina, I'm not sure how we learn as children. Right? There are all kinds of hypotheses about it, but I don't think that there's anything that's been substantiated. But this is how neural networks do it, convolutional neural networks do it. "10 seconds, guys." All right, let me end this poll. And can anybody tell me which of these statements are true? Non-distributed scanning requires the output maps of the neurons to be arranged in the same shape as the input. Just 2 and 3, right? Because if you're not looking at windows, then you can arrange them anyhow. The distributed scan is looking at windows, which means the arrangement is important. The non-distributed scan is not looking at arrangements. So only 2 and 3 are true, right? Fantastic. You guys are good. So why bother with all of this distribution? 3 reasons. Distribution forces hierarchical representations with localized patterns in lower layers, so they're more generalizable. They result in fewer computations because you can reuse computations and far fewer number of parameters. So how is that? Let's look at the first reason. Remember in the second class or even the first class how we composed a double pentagon decision boundary. Did we burden the first layer neurons with trying to detect both pentagons all at once? Or did the first layer neurons just compose? What happened? The first layer neurons found bits of the first pentagon. The second layer neurons found the individual pentagons. The third layer composed them together, right? By distributing the pattern across multiple layers, we made the problem very simple, right? And we saw that when we try to make it differently, when we put the entire burden on the first layer, the network can become impossibly large. Do you remember that? Yes or no? Right. And this is true, right? If you're trying to detect digits in these LED patterns, you'd want the first layer neurons to find individual bars, the second layer to compose them into patterns, the final layer to take decisions. So when you distribute the pattern hierarchically over many layers, your model can become much simpler and much more generalizable. So you want to encourage such hierarchical learning. It's more data and parameter efficient, which leads us to reasons 2 and 3, right? Fewer computations and far fewer parameters. Let's look at the fewer computations. First, let's look at a case where I have a non-distributed network. So the first layer, I'm trying to find patterns which are 8 inputs wide. So the first layer is looking at 8 inputs. The second layer is looking at just the outputs of the first layer. The third layer is looking at just the outputs of the second layer. So then this entire network performs this computation here. And then when I'm scanning, this entire network performs all of its computations at each position. Here I've stepped forward by 2 time steps at a time. Is this illustration making sense? That these are the computations we'll be performing, right? So now that's just one yes. Is this picture making sense to you guys? The rest of you? Okay. I'm just using the simpler picture, okay? So if I had N1 neurons in the first layer, N2 in the second layer, and N3 in the third layer, and N1 neurons were looking at 8 inputs, each of dimension D, how many parameters would I have? How many weights would I have in this setup? Guys, the first layer has N1 neurons. It's looking at 8 vectors, each of dimension D. So how many parameters does the first layer have? Anybody? How many will it have? The inputs are 8D, correct? There are N1 neurons. So the first layer has 8D N1 neurons. That makes sense? Yes, no? Now the second layer has N2 neurons and they're all looking at N1 neurons. How many neuron parameters does the second layer have? How many neurons is N2, N1, right? And how many neurons parameters does the third layer have? This guy. N3, N2, right? Fantastic. So you get the idea. That's how many parameters we need, okay? Now, let's assume a distributed network. So the first layer neurons are only looking at 2 time steps, but the second layer neurons are looking at 4 of these guys, right? So what happens? These guys are all identical, meaning these weights are the same as these weights, are the same as these weights, are the same as these weights, right? But this guy is looking at each of these outputs with a different set of weights. So if I want to see if I want to compute the total number of parameters over here, what I would have is if I had N1 neurons over here, and this is two time steps, how many parameters would the first layer neurons have? How many parameters would the first layer neurons have? Here. Anybody? It's going to be 2D and 1, right? Correct. How many parameters would the second layer neurons have? It's going to be 4, N1, N2. And the third layer neurons is just N2, N3, right? So you get it. Beautiful. Now let's compare this. So these are all the parameters you have. That's going to be 2D N1 plus 4N1, N2 plus N2, N3. Yes, the first layer has shared parameters because the first layer is scanning, right? It's looking at inputs the 2 inputs at a time, and the second layer is looking at 4 of the first layer outputs. So the second layer is effectively looking at a width of 8. That answer your question, Sriram? Yes? Okay, guys, now, if I want a standard network with the same number of parameters, here's what you're going to have. There are 4 and 4, same number of neurons. There are 4 N1 neurons in the first layer. The second layer is N2, the third layer is N3. These two networks have the same number of neurons. This one is distributed, this one is not, right? So this guy is going to have 4N1 times 8, which is 32N1 parameters in the first layer. This one has 2N1 neurons in the first layer. So do you see the difference over here? This is just 2N1, this is 32N1. The rest of them are the same, right? Yes or no? Guys, please respond quickly because I'm running out of time, right? And so you can see how this can result in a massive reduction in parameters. So now let's look at how you can save computation, right? If I have distributed computing networks and I'm looking at inputs 8 wide, then this network is scanning the input here, then it's striding by 2, and then it's scanning the input starting from here. Is there any computation that I performed when looking at this region of the input that I could reuse when I'm looking at this region of the input? Can you find any reused computation? Reusable computation? Guys, yes or no? Which ones? These three outputs can be reused, right? Because they have already been computed. And so when you actually have this distributed parameter computation network, you can see that you can also reuse the computation. And so not only do you get far fewer parameters, you're going to be able to reuse the outputs from previous positions, which means you're going to get large additional benefits in compute as well. That makes sense to all of you? Yes, no? All right. And if I do this over 3 layers, I have more examples. I'm running out of time, so I won't spend time on these examples, but it's basically the same thing. The more you distribute the network over, the more layers you distribute the network over, the greater the benefit you get in terms of the number of parameters, and the greater the benefit you get in terms of reused computation. So uh, that's for 1D scans. Same thing over here, right? If I'm scanning, then you can see that how if these guys are scanning something this sized, when I go from one position to the other, all of these can be reused, right? Same as before. The illustrations in 2D are not as clear as in the 1D case, but it's the same thing all over again. And so, in fact, we have some arithmetic. I won't go through the math right now because we're out of time, but basically what we find that in a very trivial example, if I do not have a distributed scan, I might need 1034 parameters, weights, whereas a distributed network, which is looking at analyzing windows of the same size, is going to need only 194 parameters. So the benefits can be very large. So, in fact, as the networks get larger and larger, the gains in compute and parameters can be many orders of magnitude. So distribution forces localized patterns in lower layers, which is more generalizable. You can have large, sometimes orders of magnitude reduction in the number of parameters and significant gains from shared computation. The key intuition is that regardless of the distribution, we can view the network still as scanning the picture with an MLP. The only difference is the manner in which the parameters are shared in the MLP. So the story so far, position invariant pattern classification can be performed by scanning the input for a target pattern. The operations in scanning the input with a full network can be reordered as scanning the input with individual neurons in the first layer to produce scan maps of the input, and then jointly scanning the maps of outputs by all the neurons in previous layers by subsequent layers. The scanning block can be distributed over multiple layers of the network, resulting in significant reduction in the total number of parameters and compute. So here is the final whole. $30, guys. Okay, 5 seconds. Let me end this right here. Which are the statements that are true? All of them. All no, the last one. It doesn't reduce the memory requirement because you still have to compute all the intermediate values. It just reduces the compute and the number of parameters, right? The intermediate variables are going to be the same. It's just that you have shared parameters. So some final touches, some terminology, filters and receptor fields, shrinking the maps. So you can think of the entire operation as maps of the entire image. The first layer neurons look for patterns of a small size and they scan the input and produce maps. So you can think of these first layer neurons as repainting the input with certain features highlighted. So, for example, if this guy is looking for petals, then anytime it finds a petal, it's going to highlight it and make that brighter. So each of these first layer neurons are basically repainting, redrawing the input with some features highlighted. So the second layer neurons are going to be looking at regions of the first layer neurons. And if they detect certain patterns that they're looking for, they're going to highlight those. So the second layer neurons are also repainting the input with some kinds of patterns highlighted. And then the third layer neurons, which scan the outputs of the second layer neurons, are also doing the same. So the set of weights for each of the scanning neurons is generally called a filter. Each filter scans for a pattern in the map that it operates on. And the region of the input that each of these neurons looks at is also called a receptive field. Sometimes even the pattern that it's trying to detect is also called a receptive field, but the receptive field is the region of the input that the neuron is looking at. And if you're trying to find out what pattern each neuron is detecting, it's easy for the first layer neurons. The weights of the filters will tell you what patterns it's looking for. For later neurons, later higher layer neurons, you're going to have to do some additional computation and depends on the receptive field and stride of the lower layer neurons. Then the final layer neurons are generally outputs are not kept as a map, but they're kind of straightened into a vector for further processing. So this is just terminology. This restructuring is called flattening. The other thing that many of you mentioned is as you scan, how big is the step size you take? The default step size is 1, which is why if you have a step size of 1, then this map produced by the first layer neurons is going to be approximately the same size as the input, except for some edge effects, which is why it can highlight certain patterns. But then the neurons may also be allowed to step by more than 1 pixel at a time, in which case the maps that these neurons produce are going to shrink. And the shrink factor by which they shrink depends on the stride by which the scan is performed. So CNNs with strides, when you're scanning, instead of moving forward by 1 step at a time, 1 pixel at a time, you'll be moving forward by a stride length. And the output map is going to be shrunk by a factor that's equal to the stride length. These are all just final touches. Then there's one final operation where we account for jitter, where we just say that, if the second layer neuron is saying this neuron which looks for petals must find a petal here, and this neuron which looks for sepals must find a sepal here, and so on. If this guy's output, if the petal position moves by 1 pixel, does it stop being a flower? If the petal position jiggles by just 1, no, right? So you want to account for some jitter invariance. And the jitter invariance is performed using an operation called pooling that we will see in the next class. So what exactly is pooling? In pooling, it's you'll be looking at windows of the outputs and just picking the largest value. So you would say that if I find a petal in any one of these 4 regions, I found a petal in approximately the right area. So, and I can use that to compose a flower. So pooling sort of introduces variation to minor shifts in sub-pattern positions and allows for and makes the pattern detection more robust to such variations. So here's the overall structure of the network. It has, this entire thing is called a convolutional neural network. You have neurons which scan the input, windows of the with small windows, and subsequent layer neurons which scan the maps produced by the previous layers in small windows. All the way through the network, you may have some additional components for pooling components in the middle, and then the outputs of the final layer neuron that pass through some decision mechanism. This is a convolutional neural network. This was the first convolutional neural network created for analyzing images by Jan LeCun. This is what he won his Turing Award for. So he did this for MNIST images. The first layer consisted of 5 convolutional neurons, because this first layer had 5 neurons, which we're looking at, I think, 5x5 windows. Then there was some pooling, which reduced the size of the map. Then the next layer had, I think, 10 neurons. So there were 10 neurons in the second layer, which scanned these guys to create their maps. Then there was one more pooling layer. And the outputs of these guys were put through an NLP for decisions. And it was the first time that it showed neural networks could actually work for position invariant digit recognition. So to finish our story, just ending, the scan block can be distributed over multiple layers for efficiency. At each layer, a scan by a neuron may be optionally followed by a max or pooling operation to account for deformation. For 2D or higher dimensional scans, the structure is called a convolutional neural network. For 1D scans along the time axis, it's called a time delay neural network or a 1D CNN. I'll stop here. First, did the lecture make sense?